So in electrochemistry, we have galvanic cells, and in galvanic cells, we are spontaneously reacting chemicals to form electrical energy. So this galvanic cell here is a Daniell cell where we have a zinc electrode and a copper metal electrode. The zinc electrode is dipped into a solution of zinc ions, and the copper electrode is dipped into a solution of copper ions. In this case here, both solutions are nitrate salts. To understand what's going on in this cell, we need to fundamentally look at what's happening at the surface of the electrode. So let's have a look at the zinc electrode here. And at the zinc electrode, we've got the metal of the anode there, and at the surface, we've got zinc metal atoms, and those zinc metal atoms can transfer 2 electrons to the rest of the anode. In doing so, it's oxidized to form zinc ions in solution. So what's happening is our anode is actually being consumed throughout this reaction. It's dissolving into solution. That's an oxidation reaction because we're losing electrons as depicted in that reaction there. That's the oxidation reaction, and oxidation reactions always occur at the anode in galvanic cells. So this is the anode reaction. So let's have a look at the copper side of this. So let's look at the surface of what's happening. Here's our electrode, metallic electrode. Here's our copper ions coming into that electrode, and we're going to transfer 2 electrons from that metal electrode to the copper ions in solution. That's going to reduce the copper ions and actually precipitate them onto the electrode surface, so that electrode's going to gain weight. So if we have a look at the reaction below, copper ions are going to take up 2 electrons. Taking up electrons is a reduction. So reduction occurs at the cathode electrode. So what's happening at the anode here is the zinc ions are dissolving off into solution, okay, because we're transferring those 2 electrons. So we're getting more and more zinc ions in solution. So we're going to build up a positive charge in that anode solution there. So that's going to cause some electrical instability, and that's actually going to attract the nitrate ions from the salt bridge. So nitrate ions are going to start moving towards that cell, and nitrate ions from the copper solution are going to migrate through to that cell. The positive charges of the zinc are going to try and move into that salt bridge, and the sodium is going to be kicked out and move towards cathode. So here we have cations moving towards the cathode. If we have a look at the copper cathode side, what's happening there is our copper ions are accepting those 2 electrons, and more and more copper is going to be consumed from that solution. So overall, it's going to leave the solution negatively charged from those nitrate counterions. Those nitrate counterions are not going to be happy where they're sitting. They're going to attract the sodium ions to try and neutralize that charge. The positive charges of the zinc ions are going to try and move into there, and also those nitrate ions are going to try and move into that salt bridge and move across to the anode. So those anions are going to move towards the anode cell. If we have those zinc metal atoms on the surface of the electrode, what's going to happen is going to donate those electrons to that surface, and then another zinc atom might donate its electrons to that surface, to that electrode. So we're going to build up a negative charge from those excess electrons on that side, on that anode. So the anode is going to be negatively charged. Because we're taking electrons off the cathode to reduce our copper, that's going to leave an increasing concentration of positive charge because there's a deficiency of electrons on that electrode. So we're going to have electrons moving from the anode to the cathode side through that external electrical circuit. So let's have a look at those 2 reactions. We've got the anode reaction, we've got cathode reaction. It's not very pleasant to actually draw this whole cell out. So how can we do this? We can do it with a cell diagram. We've got zinc metal solid with a phase boundary to zinc ions in solution, and they're going to be at a specific concentration, so we can write that. And then we're going to have a salt bridge connecting the 2 half cells together, and we can represent that with the double vertical lines. On the other side of the cell, what are we going to have is we're going to have a copper metal electrode, and that's going to be a solid, of course. There's going to be a phase boundary between the solid and the solution, so we're going to have copper ions in solution there, in contact with that. It's going to be an aqueous solution. There's going to be a certain concentration of those ions, and then we're going to have, of course, the salt bridge, which is depicted by those double vertical lines. So we could put those two notations together and develop an overall cell diagram or cell notation for this whole entire cell. So we've got the solid zinc in contact with the zinc aqueous zinc ions at a particular concentration. We've got a salt bridge there. We've got copper ions in contact with the copper. They're going to be at a particular concentration, and our solid copper electrode. So that's going to be our overall cell diagram for this Daniell cell. And we can see as we've written it there, it's going to be written down as it's going to react. So we're going to have zinc going to zinc ions in exactly the same way as our reaction down below there. And we're going to have copper ions going to our copper metal, just as we had in our reduction reaction. So this is going to show the anode on the left-hand side and the cathode on the right-hand side. And from knowing which side is the anode and which side is the cathode, we can say the anode is negatively charged and the cathode is going to be positively charged. So now we don't have to draw out this big entire diagram or the reactions below to understand exactly what's happening in this cell. We can just use this cell diagram.